Just the microphone for the recording, but not the one for the room. Well, it's great to have you all here. And we'll start this Algebraic Geometry in Mexico 2017 conference in Oaxaca and PXM with Juan Manuel Burgos from Mexico, Ciencias, and he's going to be speaking about Teichmuller theory of the universal hyperbolic lamination. Juan Manuel?
Thank you very much, Ernesto. Well, first of all, it's a great pleasure being here today. It's mostly a great honor being the opening band of the event. So thank you very much, the organizers. This is a joint work with Professor Alberto Berkowski. He will be here on Saturday. And I'd like to comment about some very fresh cookie result we just got. Just to motivate, let me say, very general and well-known material to motivate the problem. Consider a holomorphic covering of Riemann surfaces, a genus G prime curve covering a genus G curve holomorphically, and well, ranging over all the complex structures of the genus G curve, the pullback map defines a holomorphic map between the corresponding moduli spaces. And of course, the relation of the genus is through the degree of the map P by the following formula. Very basic stuff. And in particular, if the embedding of the moduli is not the identity, we have this relation here. What it is really interesting is that this bound is optimal. Optimal for genus G greater than or equal 6, and it is the content of the Aramagiana-Soto theorem. It's a very strong rigidity result. And the moral of this is that holomorphic maps between moduli spaces is a very delicate thing, because a priori you have enough room for embeddings, but it turns out by the theorem that there are none of them if the constraint is not verified. So, and well, with this in mind, we prove the following: that there is a branch holomorphic Keller isometric covering, covering in the sense in the orbifold sense, for every genus greater than or equal to, and this covering factors through the alternate product of the genus 2 curves, of the moduli of genus 2 compact curves. And actually, this is a corollary of the following result. Respect to the respective Weil-Peterson metrics on the Teichmuller spaces, there is a Keller isometric biholomorphism between the G-1 times copies of the Teichmuller space of genus 2 curves and the Teichmuller of genus G curves. And moreover, this is a corollary of the main results of our work. There is respect to the renormalized Weil-Peterson metric, there is a Keller isometric biholomorphism between the Sullivan's Teichmuller space of the universal hyperbolic lamination and the continuous function of the profinite completion of the genus 2 curve fundamental group and the Teichmuller space of the genus 2 curves. That's our main result. And moreover, in a sense, I will explain at the end of the talk, this result is functorial in respect to to the inverse limit maps of the profinite completion.
What is it? C? Continuous?
Continuous. C is continuous. Well, just to fix common language and notation, let me talk about very well known and standard material, but it's just to fix notation. Consider a Riemann surface sigma. How we deform its complex structure? Well, we are looking for the construction of the moduli space. There are mainly three ways of constructing moduli space. One is through Hilbert schemes and geometric invariant theory. The other one would be via Torelli maps and Jacobian varieties. We will follow the Teichmuller approach. So consider the Poincaré uniformization and the representation of the deck transformation, that is a function group representation into the hyperbolic isometries of the Poincaré disk. It's a faithful representation. And geometrically, a picture one should have in the head every time we talk about deck transformations or function group representations is tessellations. This is the tessellation of the genus 2 curves, this is the tessellation of the 1 cusp torus, and the tessellation of the 3 cusp torus. We will focus mainly on the first case, on the tessellation of the genus 2 curves, because we don't want parabolic elements in our function group. We don't want elements like this, cusps like this. Well, an L infinity 1, minus 1 differential along the top will be called just a differential. We will say that mu is a G automorphic differential if it is a differential and it is invariant under translations of the function representation. And we will denote the space of all those differentials, L infinity G. And we will say that mu is a Beltrami differential if its supremum norm is strictly less than 1. And these are the important guys because this will be our deformation parameters. And just a remark, the pullback of a differential in the curve lifts to the disk as a G automorphic differential in the Poincaré disk. So now we have our deformation parameters, how we actually realize a deformation with a given parameter. And well, a Beltrami differential can be seen as an infinite measurable field of ellipses, actually a measurable field of class of homothetical ellipses. We don't care about the radius, only the eccentricity, the relation between the major and minor axis. And this is how the Beltrami differential, the mu, encrypts the ellipse data. Consider the Alfors-Verse equation. Alfors-Verse equation in the weak sense, in the distributional sense. And a natural question is there a solution in the Poincaré disk of this equation? And geometrically speaking, it is equivalent to ask if there is a map straightening all the field of ellipses into infinitesimal circles. That's the equivalent notion of a solution. As you remember that the field of ellipses is L infinity. It is not continuous, and at first sight there is no right for the existence of an F like that. And well, it results that the Alfors Burgos' theorem answers positively our question. There are quasi-conformal homeomorphisms. There are not only solutions, but they are homeomorphisms to the Alford-Burgos equation, and moreover, these solutions uniquely extend to a homeomorphism on the boundary of the disk. And there is a unique solution fixing 3 arbitrarily points. We completely arbitrarily fix 1, I, and -1. We will call a solution like that a canonical solution. Remark, if the differential is G automorphic, the solution will be G equivariant. If mu equals 0, then we have Cauchy-Riemann equations. In the weak sense, by Weil theorem, F is a holomorphic solution in the strong sense. And there are non-trivial, by holomorphism, non-trivial automorphisms of the curve, and there are at most 84 times G minus 1 of them. It's an open problem to know at which particularly G's this is an equality. That's an open problem. Well, in particular, abusing of notation, for every differential, for every Beltrami differential, we have a quasi-conformal deformation. And finally, we deform the complex structure in this way. Given a complex structure, we deform it like this, and the resulting curve will be called the deformed curve. Well, equivalent, we can write it in the complex structure. And a natural question, are we really deforming? Is there redundancy in the parameters? And we say that 2 deformations are equivalent if the following triangle commutes, and H is an orientation-preserving homeomorphism. The equivalence classes constitute a coarse moduli space of the genus G curves. It is coarse because of the thing I said before. We have non-trivial automorphisms, so there is no universal family, and we don't have a fine moduli. And to produce a fine moduli, we strengthen the relation. Instead of taking a homeomorphism, we take a homeomorphism isotopic to the identity, and that will be the Teichmuller equivalence relation. And this is a very useful characterization of the Teichmuller relation. 2 deformations are Teichmuller equivalent if and only if the canonical solutions coincide on the boundary. It's a very useful characterization. Well, the above condition defines an equivalence relation in the space of Beltrami differentials. And because of all previously said, we have the Alford-Burgos analytic model of the Teichmuller space. It's a deep theorem, very deep theorem, that the Teichmuller space is a complex domain of complex dimension 3G minus 3. Very deep theorem because the moduli space, it's an orbifold. We have these orbifold points that don't allow us to work very comfortably. And the Teichmuller space is just a ball in complex space. It's the nicest thing you can think of. Well, and naturally, the relationship with the moduli space is like this. The quotient of Teichmuller space by the mapping class group action gives the moduli space, and the mapping class group is the quotient of the positively oriented homeomorphism, quotient the isotopic to the identity ones. And if we see the moduli space as a stack, we can say that the mapping class group is actually the fundamental group. If we forget about the function representation, I mean forget about the tessellation and the curve, and we repeat formally all the previous construction, we get the universal Teichmuller space. And it is useful because it is universal in the sense that it contains all of the previous finite dimensional Teichmuller space. The problem is that this space is too big. It is a non-separable space containing all of the previous finite dimensional ones, so a natural thing to do is, well, to see if there is something in the middle. We put this information in the freezer for a while, and now we talk about what the hyperbolic lamination is. Consider the inverse system. I am in the preliminary section. I'm still talking about preliminaries. Consider the inverse system of finite index subgroups of the fundamental group. G will denote along all the talk the fundamental group, and the inverse system with its inclusions. Then for every finite index subgroup, consider the diagonal action on the pile of disks. And the quotient gives a Riemann surface, so we have the functor that for every finite index subgroup gives me a finite holomorphic covering of sigma. That is because the functional representation, the diagonal action is equivariant with respect to the functional representation. And because all of these constructions are functorial, we actually have an inverse system of finite holomorphic coverings. That's the picture you should have in your head, the tower of finite holomorphic coverings. Well, we want to take the inverse limiting here. But first, consider the profinite completion of the group G. Is defined as that inverse limit, ranging over all finite index subgroups. And because the function group is residually finite, the completion is a group extension, and we have a dense immersion. The collection of all finite index subgroups is a neighborhood system of the identity, and by translation it defines a topology on the group whose completion is the profinite completion just defined. And as a topological space, this is nothing else than a Cantor set. You can think of the Cantor set you like most, and G infinity will be homeomorphic to that because of the universality of Cantor sets. What really distinguishes one Cantor from another is its group structure. Topologically, they are all the same. And the group G infinity is an ultrametric space. It has an ultrametric metric. It is constructed like this. Consider the cofinal inverse systems of normal subgroups such that each normal subgroup is the intersection of all subgroups of index less than or equal to n. And that defines a valuation on the group. With that valuation in the very well-known standard procedure, we construct the ultrametric metric. Just a comment. Don't get confused of this theory with geometric group theory. This has nothing to do at all with the Cayley graph. To see the group structure with the word metric has nothing to do with this metric. In the Cayley graph, the Cantor structure is at the boundary. And here, the whole group is a Cantor set. So it really has nothing to do. Well, by the functoriality of the construction, we get this. We define the universal hyperbolic lamination as the inverse limit of the finite covering tower. And by functoriality, we have that expression in here. This is the pile of disk with G infinity as the fiber, a Cantor set fiber, and the diagonal action. And this is a lamination whose leaves are densely immersed disks. The leaf space is the quotient of the profinite completion, quotient the group. And people familiar with the Kronecker foliation, the irrational slope foliation on the torus, will immediately recognize the problems on this space. This is what is called a bad quotient, because from its topology, almost nothing is recovered. You get stuck in there. But in the non-commutative geometry context, if you see this space as a groupoid, encrypting the quotient data, you can calculate the convolution algebra, and that will be the non-commutative model of this space. And it's a very powerful. It's a very powerful thing in the Kronecker foliation. The convolution algebra of the leaf space gives you nothing else than quantum mechanics. You get the Heisenberg relations. So it's a very interesting question to calculate the convolution algebra of this space. What it should be. I don't have any idea of what is the convolution algebra of this. And the following is a picture you should have in mind of the lamination. I like to think the hyperbolic lamination as a borrowed genus 2 surface with fiber the Cantor set G infinity. If you make a zoom of that fuzzy curve, you see the Cantor. But the monodromy, it's very well. The monodromy of the lamination is a group structure of the profinite completion. Well, define the base leaf of the lamination as a distinguished leaf. That is the following one. It's a leaf that contains the neutral element of the group. And define the embedded disk as the disk, but with the coarser topology, that is the initial topology of the embedding topology of the base leaf. And its basic open sets are those sets in there. This is a picture like this. Have the Poincaré disk, the fundamental domain, these are geodesics in the disk, blah blah blah. And a basic open set will be something like this. This is the U. And it repeats itself countably many times, accumulating in the ideal boundary. Well, and by definition, with this topology, the base leaf is an embedding, and because the identity map is continuous, we have an embedding of the continuous functions of the embedded disk into the continuous functions of the disk, and this will be called the limit automorphic functions. And what limit automorphic functions are good for? They are good for the following. we can see a function is limit automorphic if and only if it is a pullback by the baselif of a continuous function on the lamination. So instead of thinking about continuous functions on the lamination, you just think about limit automorphic functions. That is much easier. And well, item 2 just justifies the name for these functions. It is limit automorphic if and only if it is the uniform limit of an automorphic net. And well, from now on, I will talk about new stuff that we need to prove our main results. We finished the preliminaries. And well, we have this chain of proper inclusions. And Dennis Sullivan defines his Teichmuller space of the lamination as the closure of the inductive limit. What we want to do now is to reproduce the theory of compact Riemann surfaces to the category of compact laminations, compact Riemann laminations. That is what we want to do. And in particular, we want an Alfors-Verse model, an Alfors-Verse analytic model for this space. That is what we are looking for. And for that, we need these objects in here. Consider the representation of the fundamental group in the space of L infinity of differentials. And the representation is just a pullback of the functional representation. And a differential whose orbit is continuous with respect to the profinite topology of G will be called limit automorphic. And the space of limit automorphic differentials will be denoted by L infinity delta embedding. Don't take this literally. This is just notation. This is nothing else than notation. In concrete, that definition means the following. Just to assimilate the definition, consider the following very simple example. Consider the real line acting on the space of L infinity functions on the real line just by translation. So an element of L infinity will be the orbit of an element of L infinity will be continuous with respect to the translation action if and only if it has a uniform continuous representative. So we are codifying the continuity notion via an action. That is very useful because we are not in a space of functions, we are in a space of equivalence classes, so we need that technicality. Well, the space of limit automorphic differentials is a Banach subspace of the space of differentials. And proposition, the following is an analytic model for the Teichmuller space in the category of Riemann laminations and is equivalent to Sullivan's Teichmuller space. I mean, you can construct in the same way as we did before in the classical category of curves, the same construction, but in the category of Riemann laminations. You will get a Teichmuller space, a moduli space, a mapping class group, all the same. What we say is that the Teichmuller space you construct in that way coincides with the Sullivan's Teichmuller space, and now we have an Alfors-Verse model for that, relating those models. Well, the next problem is what metric should we put on the Teichmuller space of the lamination? And this has several problems. The first problem is that you naively could think that the Weil-Peterson metric on the universal Teichmuller space, the T1 I defined previously, works in the Teichmuller space of the lamination. Well, it is completely false because of a very basic thing. The Weil-Peterson on the universal Teichmuller space is not even defined. It works only in what is called the smooth Teichmuller space. That is the one characterized by this condition, that the infinitesimal deformations are C3½ plus epsilon smooth. Well, a second approach would be consider two limit automorphic differentials, consider the respective nets of automorphic differentials converging uniformly. At every stage you have a Weil-Peterson metric and you just take the limit. Well, that limit gives you nothing because it is 0 or it just blows up to infinity. So it cannot distinguish anything. And so we defined what we call the renormalized Weil-Peterson metric. That is the same idea as before, taking the limit, but at every stage we renormalize by the index of G' in G, the index of the subgroup. And well, theorem, it is well defined. It doesn't depend on the automorphic nets of the chosen automorphic nets, and it converges for every pair of limit automorphic differentials. So now we have a good degenerate metric in L infinity and a well-defined metric in the Teichmuller. Of course, it has the same problems as in the classical case. It is not a complete metric, but it is complete in the convex sense. I don't know how to say it. It is convex complete. For every pair of points, you have a unique geodesic, but it is not geodesically complete. By Hoff-Renow, it is not topologically complete either. So, well, an important remark: the metric we just construct is an extension of the classical Weil-Peterson metric on G-automorphic differentials. As a non-trivial immediate result of that construction, we have a generalization of the Nack-Berkowski embedding. Consider the complex analytic quadjoint orbit, and well, it's a theorem that it embeds holomorphically and Keller isometric in the universal Teichmuller space, and it generalized the previous result that it is transversal to the Teichmuller space of the lamination. And well, finally, we are in position to enunciate our main results. Theorem A, the one I talked at the introduction, respect to the renormalized metrics, renormalized Weil-Peterson metrics, there is a Keller isometric biholomorphism. And this result can be seen as Keller coordinates of the Teichmuller space of the lamination. Well, Teichmuller valued Keller coordinates. And it has the very nice properties that these coordinates are functorial in this sense. Functorial in the respect to the inverse limit maps. Well, idea of the proof. For every differential, define the function that at each group element you take the respective translation by the faction representation. Lemma: the differential is limit automorphic if and only if this map, just defined, continuously extends to the profinite completion. That's a very useful characterization. Remember this notation. The hat will be the continuous extension to the profinite completion. Consider a fundamental domain, something like this, of the G action on the disk. And because of G equivariance, the product will be a fundamental domain of the diagonal action of the bundle. And define the following map, map from this continuous functions space into the limit automorphic differential space, such that given a continuous function, xi, you will get a limit automorphic differential satisfying this property here, that they coincide in the fundamental domain. We define the Weil-Peterson metric on the continuous space functions as usual. Here the measure is the Haar measure, the unique normalized Haar measure on the profinite completion group. The finite completion is a locally compact group, so it has a Haar measure. And lemma, this is the main lemma of the main theorem. Respect to the Weil-Peterson and renormalized Weil-Peterson metrics, the map F is an isometric isomorphism. And well, finally, recall that the set of limit automorphic differentials equivalent to 0 equals the set of renormalized Weil-Peterson null vectors. Actually, this is one of the motivations for defining Weil-Peterson metric. It's a characterization of the equivalent to 0 differentials via geometry, via a metric. And well, because of the lemma, these null vectors are mapped one-to-one, so the map F descends to a map in the Teichmuller spaces. And that's the theorem. And we'll recall theorem B, the G-1 times alternating product of the moduli space of genus 2 compact Riemann surfaces is a complex analytic Keller isometric branch covering. Recall that everything is in the orbifold sense again of genus G compact Riemann surfaces. And the idea of the proof is to use Masur-Wolf theorem. It is the analog of Royden's theorem for Weil-Peterson metric. It says that the mapping class group of a surface is isomorphic to the positively oriented Weil-Peterson isometries of its corresponding Teichmuller space. And then by theorem A, it's a very simple thing to do the math in here. We have the following subgroup of the mapping class group. And in particular, we have the following branch covering. Recall that the moduli space is just the quotient of Teichmuller space by its mapping class group. So we get the result. And thank you very much.
Universal factor space.
Yes.
You also have a associated moduli space corresponding to that
Uh,
limit of the other ones that constructed, or is that all direct?
No, there is no analog of universal moduli, but there is an analog of moduli of the lamination, and it goes like this. Recall that you can do the parallel construction we did in the category of Riemann surfaces in the case of Riemann laminations. So it is natural to have a Teichmuller space, and it is natural to have a moduli space. And the relation is the same. The moduli space of the lamination equals the Teichmuller space of the lamination, quotient the mapping glass group. And the very interesting thing in here about the mapping glass group, this is a theorem of Chris Oden, it is isomorphic to the group of virtual automorphisms of the fundamental group of the surface of the surface. Recall that you have the lamination, and it covers the base, the genus 2 surface. And this is the moduli space you were asking for.
Any other questions? Well, Juan Manuel, thank you very much.
Thank you.
And we have a 5-minute break.